Hi, in this video, we will learn about the physics of waves and sound. So we will talk about waves, types of waves, waves on a string, and sound waves, sound intensity, Doppler effect, and also standing waves. So let's get started. A wave is a disturbance of that propagates. It means just goes in one direction from one place to another. So it's a disturbance that goes from one place to another. Waves occur in a medium such as air, water, solid, spring, or strings. There are different waves. There are different types of waves, and some of which are transverse waves, where the particles move. So if the wave is propagating in this direction, but the particles of the wave that make up the medium, they move in perpendicular direction. So that's transverse direction. So these are called transverse waves. Or there are longitudinal waves where the wave propagation is in this direction. And the particles in the medium, they oscillate back and forth in the same direction of the propagation. So if you look at some of the points here, for example, this point, this particle, it doesn't really move across the whole distance, but it just oscillates at the same point. But the wave itself, it's the disturbance, it's the change of pressure, which we can think of that in change of pressure or density. It moves in the forward direction. So we are interested in the movement of not the particles, but the disturbance or the wave itself. Or we can have water waves, like the surface waves like these. And we will learn that these water waves are actually a combination of transverse waves and longitudinal waves. It's important to distinguish between the motion of the wave itself and the motion of the individual particles that make up the wave. For example, if you look at this wave that's created by these people, the wave propagates in this direction. So in the animation, the stick figures are not moving. The individual particles here, the stick figures, they are not moving in the forward direction, but the wave does move in the forward direction. So we should distinguish between the motion of the wave and the motion of the individual particles. As we saw here, the individual particles, they move in the transverse direction in transverse waves. In the longitudinal waves, they don't move all the way through the distance, but they just oscillate in the longitudinal direction. Water waves, they go around a circle, but they're still not really moving. But in each case, the wave itself, it moves in the forward direction. It can move also in the backward direction as well. So let's start with transverse waves. The particles of the medium move in the perpendicular direction to the direction of the wave propagation. So if you create a wave like this, it's moving to the right. But the particles, which are, in this case, the atoms of the string, they move up and down in the transverse direction, so this direction is the transverse direction because it's perpendicular to the propagation. So you can create these waves by fixing one end of the string on the wall and basically just shaking the other end of the string. And if you look at this figure, this animation here, the wave, the direction of the propagation is in this direction. And if you look at this black dot, it moves up and down in the transverse direction. So particle motion is in this direction, which is the transverse direction. So these are the transverse waves. The other example is, again, the Mexican wave that you see in the stadiums. The people here, the particles are the people, they move up and down, but the wave itself moves in certain direction, which is perpendicular to the up and down direction. The other types of waves are longitudinal waves. In longitudinal waves, the particles of the medium move in parallel to the direction of the wave. So if you look at the disturbance that moves in this direction, and the particles, for example, take this black dot here, what happens to it? It basically oscillates back and forth as the wave moves forward. So the particles are not moving from here to here, they're just oscillating at their position. So they're oscillating back and forth at the position where they are. The other example is to the longitudinal waves are the waves on this spring. So this is again the pressure wave. The spring is not it's not oscillating up or down. It's actually the pressure is in the forward direction. So the pressure or the wave. So the wave is in the forward direction, and the particles of the spring or the sections of the spring are also moved back and forth around certain equilibrium point. So we can create longitudinal waves by a speaker. In fact, the sound waves are also longitudinal waves. So if you create this pressure, what happens is certain parts of the wave, like this part, which is shown by wave, this black arrow, those parts, they have more air because there's compression. So the air is denser here. So these are compression areas. So there's more air here. In certain airs, like here and here, the air is less dense, so there's less pressure. And these areas are called rarefactions. So of course, this looks like, so the wave moves in this picture to the right. There's this loudspeaker here. So this picture is two-dimensional, but you can think of this as a column of air, three-dimensional. And we can show the compression points and the rarefaction points. So more air or denser, less dense, dense, less dense. We can show these points by a one-dimensional wave as well. So these top points would correspond to dense air positions, and these minimum points would correspond to less dense or rarefaction areas. So when we talk about a wave, when you see this for a longitudinal wave, it doesn't mean that the wave is actually going in the transverse direction. It's pressure waves. So as you can see here, it's not going up or down. It's going in the disturbance is going in the forward direction, and the particles are just oscillating. But what we can show with this sine or cosine plot, one-dimensional, we can show where the density becomes maximum and the density becomes minimal. So again, look at these red dots. So some of the particles are just marked. So, and if you look at them, they don't move across the whole distance. They just oscillate back and forth at the same around certain point. But the wave itself, it propagates forward. So it goes forward. So when you listen to a music, let's say you are listening to the music here, the air particles from here does not come all the way to your ear. So what you are hearing is this wave, this disturbance, this density or pressure difference that moves. So if you look at the air particles, they don't really move much. They're just oscillating. So what you hear is the disturbance in this medium. Okay, third, water waves. Water waves are a combination of transverse and longitudinal waves. So particles in water waves, they move in circles. So in the transverse waves, if the wave is in this direction, in the transverse case, the particles in the medium would move up and down. So in the transverse case, in the longitudinal case, if this is the direction of the wave, the particles would move right, so they would basically oscillate. So the water waves are a combination of these two, because if you look at any particle, for example, track this one, it actually goes around a circle. Or you can look at other particles, they go around a circle. So a particle is not really moving across the surface. So what moves is the disturbance, the wave itself. But the particles are pretty much, they don't really leave their position. They just make a circle around that position. So let's go over some of the important concepts or definitions. First of all, if you have a wave, the maximum points are called crests, and the minimum points are called troughs. So the wavelength is basically that the definition of wavelength, lambda, is distance over which wave repeats. So it's basically, you can measure it as from one crest to the next. So this would be the wavelength, or you can measure it from one trough to the next trough. So these are the same distances. If you look at here, in this longitudinal wave, the wavelength is the distance between two compression points. So if you look at this compression point and this compression, of course it moves, but so these two, for example, or these two, the wavelength is approximately this much. So what about period? It's the time for the wave to move for a distance of one wavelength. So if you have a wave like this, so this could be a transverse wave, or this could be showing, it could be showing the maximum points, the compression points of this wave. So the point here is, though, if, so the period is, the definition of period is the time that it takes for the wave to move for a distance of one wavelength. So if you look at this wave, let's say from this crest to the next, this is the wavelength, this is the distance. Now, if the wave moves for this distance, we can maybe track this point. So let's call this point A and this point B. So A comes here and B comes here. So basically the wave moves for a distance of one wavelength. The time that it takes for that movement is the period. And the definition of frequency is just inverse of the period. So frequency is equal to 1 over t. And finally, the speed of wave. So the speed of this wave, you can track this, this word wave here, the black arrow that give you the speed of black arrow is the speed of the wave. You can find it from the formula, distance divided by time. Here, the relevant distance is basically the wavelength. And the wave, by definition, it moves the distance for wavelength in how much time, that will be the period. So if you divide it by distance divided by time, wavelength divided by period, and period is 1 over period is the frequency. So I can write this as wavelength times frequency. So if you want to find one of these things, the speed of the wave, the wavelength of the wave, and the frequency of the wave, they are related by this relation. Okay, let's look at this exercise. sound waves travel in air with the speed of 343 meter per second. So this is the speed of sound in air. Medial C on a piano produces, so medial C is this note. It produces sound waves with a wavelength of 1.31 meters. What is the frequency of medial C? So if you want to find the frequency, again, we just learned about this relation. So we know the speed of air. Why do we use the speed of air? Because the piano, when you play it, the sound, it's basically the movement in air, so we have to use the speed of air. And the wavelength is given, 1.31. So this is given. So what we're going to find is the frequency. And if you do this division, then you find this frequency. The frequency that corresponds to this wavelength is 362 hertz. And remember, hertz means 1/2. Okay, in the second part, the problem says dogs can hear sounds with frequencies as high as 45,000 hertz. What is the wavelength of such sound? So now what's given here is the frequency. We know the speed of air. Now what we're going to find is the wavelength, lambda, of that the sound that dogs can hear, which corresponds to this frequency. Again, we are using the same equation. This time we are trying to find lambda. So if you again do this division, so the speed of air is fixed, it's this number, divided by the frequency, you will find the wavelength of that frequency is 7.62 millimeters. So that means at every approximately 8 millimeters, so the wave difference between those maximum density points is approximately 8 millimeters. But in the case of middle C note, the difference between those maximum points, the maximum pressure or maximum density of the air, of the sound, the distance here is 1.31 meters. We can hear the sound, this frequency, but we cannot hear this one. Okay, so let's move to waves on a string. So we talked about the waves in air. Now we're going to talk about waves in a string. The speed of wave is determined by the properties of the material through which it propagates. For a string, the wave speed is determined by the tension force in the string. So the tension force in the string, you can increase that tension force by tuning your guitar. You can decrease it, you can increase it. And the second thing that the wave speed depends on is the mass per length. It's shown by mu, and it's the total mass of the string. So take one of these strings, the total mass divided by total length. So it's basically how much mass, how many kilograms is this string per 1 meter. So these two determine the speed of the wave on a string, and the formula for that is this one. So this is again the tension on the string, and this is the mass per length. You can think of mass per length as the density of the string. The wave speed increases when the tension increases, as you can see, because it's in the numerator. If this increases, then the speed increases. And it decreases, the speed decreases when the mass per length increases, because it's in the denominator. And it makes sense, because if the string is heavy, then it will be for the wave to travel, it will be harder for the wave to travel, so it would have smaller speed. Okay, in this exercise, it says a typical guitar string has a mass per length of this number and is tightened to a tension of 71.4 newtons. What is the speed of waves on the string? We are going to just use this formula. So the tension is given, mass per length is given. If you plug in those numbers, you find 422 meters per second. This is in fact more than the speed of sound in air. So it's more than speed of sound in air. Because in air, if you remember, it was 343 meters per second. Okay, so the waves can reflect from walls or other obstacles. So when a wave reaches the end of a string, in the context of strings, let's say there's a wall, it will be reflected. So if the end of the string is fixed, as you can see here, the reflected wave will be inverted. So it's on the top as it moves, but when it's reflected, it goes in the bottom. In the second case, what we have is we have something like a ring here that can go up and down. So it's not fixed, it's kind of free to move. If the end of the string is free to move transversely, so yes, it can move freely in the transverse direction, the wave will be reflected without inversion. As you can see, it's on the top, and after the reflection, it's still on the top. In chapter 13, we dealt with time motion of one object, which was the oscillator. So we had an oscillator, and it would move back and forth at the same place, right? The oscillator would not travel in any direction. It will be fixed. It will just move back and forth, and we had only one oscillator, not many. So we had plotted the amplitude versus time. So the amplitude was how much this oscillator, how long this oscillator goes forward and backward. So we plotted the amplitude versus time graph, as you can see here. So this is the amplitude. It can go to 4 at maximum and -4 at minimum. And in the x-axis, we use time. So that was it. So the object did not have linear movement in one direction. So we did not really use the x coordinate. I mean, here, x, it just simply means the amplitude. But the only variable, independent variable, was t. Here, instead of x, I used y, but it's still the wave height at time t, or wave amplitude. So the object did not have linear movement in one direction, but only oscillated at the same place. But if we think about the waves, they are not just like one oscillator. They're actually, you can think of waves as there's an oscillator at every point. So there are millions and millions of oscillators, and the oscillators, they don't only oscillate in time, but they also depend on x, because they would have position. Of course, if it's a two-dimensional, it would have x and y. If it's a three-dimensional wave, it would have x, y, and z as independent variables as well. So waves composed of not one particle, but many particles spread over space. They are spread over space. So we should talk about the amplitude of the wave at time t and position x. So for the harmonic oscillator, the only independent variable was t, but here, since now the wave is spread over space, there will be also the position x in addition to t, and here y is the amplitude. So y is amplitude, x is the independent variable for the space, and t is the independent variable for the time. So what is the meaning of y? So we said it's amplitude, but in terms of what is the physical meaning of it? Well, for transverse waves, this top case, this y is the wave height. So we can think of y as how much the individual particles goes up and down. And for the longitudinal waves, it's the particle density. So this function for the longitudinal waves would give us the particle density or the pressure at any time, at any position on this line. So what is the equation that shows the amplitude at any position x at any time t for a harmonic wave? So remember, harmonic meant either sine or cosine. So for the harmonic oscillator from the chapter 13, we had for amplitude, so this was the amplitude. And this was the functional form that depended on time, and this would be the period, and this would be the amplitude. So this function would give me wave height or amplitude at any time t. So as I mentioned in the previous slide, now for the waves, since they move in space, their function should not only depend on t, but also it should depend on x. So we will have pretty much the same thing, this part here. So this time-dependent part is already here. So we have the amplitude, we have the cosine, and this part are the same. But what we have to add is also the x dependence. Now, if you look at the dimensions, this is 2 pi is just a number. It doesn't have any dimensions. And time divided by period is dimensionless. And so everything inside a cosine should be dimensionless. So this part is fine. And if you look at here, again, 2 pi is dimensionless. X is in dimensions of distance, and also lambda, which is the wavelength, is also in dimensions of distance. So this part is also dimensionless. So this is the correct functional form for a wave. Now, if you're wondering about this negative sign, it just gives us the waves that move in the positive direction. If you make this sign positive, then you get waves that move in the negative direction. So we can also rewrite this as by using the common parentheses for 2 pi divided by lambda, you would get this form. And if you remember from the previous slides, this is like x divided by time, distance divided by time, which gives you the speed of the wave. So the wave can be written also in this form. So here you can see that the wave is moving forward. So to notice that the wave is moving forward, you can concentrate on this dark blue section. If we highlight it like this, you can see that it's actually moving forward. And you have to notice that the wavelength is something that it has something to do with the space. So it's the distance from the crest to the next crest. And the period, it has something to do with the time. So it is the time for, again, let's call this A point, B point. So A comes to where B is at this time, and B comes at this point. So when the wave moves for a distance of one wavelength, see A goes from here to here, so A is now here. The time that it takes from here, t equals 0, to this time, it's the period. So again, lambda the wavelength has something to do with space, and the period or the frequency, which is equal to 1 over frequency, it has something to do with time. Here we have a three-dimensional plot of traveling cosine function for all positions x and all times t. So the vertical axis is for the amplitude, and the other axes are for time and position. So the wave is at this position around, let's say the second crest is at 10. And so that's for t equals 0 time. When t equals 1, what happens is to the second crest, it comes here. So the second crest at time equals 1 is around x equals 20 points. So this point is actually x equals 20. And the wave moves on. So again, the wavelength it's related to position. So it's the distance from crest to crest. And the period, it's related to the time. You can see that it's on the time axis. It's related to time. It's the time for the wave to move for one wavelength of distance. So this function gives the amplitude of the wave at all positions and at all times. So if you want to find, let's say, y equals, what is the amplitude of the wave at x equals 15 when the time is equals 0. So that will be the minimum. So let's say the minimum is -1 for the amplitude and the maximum is +1. So that could be -1. Or we could ask, what is the amplitude at x equals 20 and at time equals 1. So I have to look at this one. So at time x equals 20, so it's this point, so it's the +1. So for time 1, it's +1. So basically this function gives all the information about the wave. So it gives you the amplitude at all points at all times. Of course, the amplitude as time changes at any given point. For example, if you take x equals 20 again, so the amplitude when time is equals 0 is +1. But if the wave moves a little bit, let's say it's after some time, the wave will move. Maybe we can plot it like this. So after some time, the amplitude at x equals 20 will not be 1. So the point here is the amplitude not only depends on space, so it's different at different points in space, but it also depends on time. Again, the period is the measured, so the period is measured in time, wavelength is measured in space, and the wave speed can be found by the wavelength divided by period. Okay, so let's move to sound waves. Sound waves are longitudinal waves. The wave speed in air is about 343 meters per second at 20 centigrade degrees. If the weather temperature is different, then this number would be a little bit different. So again, we can think of a loudspeaker. So this is the diaphragm of the loudspeaker. It can create pressure on air, so it could create longitudinal pressure waves, which is the sound waves. So these dense points can be shown by sine or cosine like these. So the maximum points would correspond to dense points or compressions in terms of pressure. If you talk about pressure, though, you can think of them as the compressions. And these rarefactions, these points, they would correspond to less minimum density points. And in terms of pressure, those points will correspond to minimum pressure points. So in a sound wave in air, it's not the air molecules that are transferred for long distances. As you can see, the individual particles only oscillate back and forth a little bit. So it's the compression that propagates with 343 meter per second. Also, we hear the compression and rarefaction differences. So here's the compression, here's the rarefaction, and that moves, that disturbance is moving. So what we hear is the density pressure changes. Sound doesn't propagate only in fluids. When we say fluid, we mean two things, liquids or gases. It also propagates, sound also propagates in solids. So you can actually test this. You can put your ear on the table and hit the table. You will see that it's the sound actually propagates in solids pretty well. The speed of sound is different in different materials. In general, the denser the material, the faster the sound travels through it. So we talked about air at 20 degrees, it's here. At 0 degrees, it's the speed is just a little bit less. But if you look at, for example, helium, hydrogen, fresh water, plastic, steel, granite, and if you go up, so these are like gases, fluids, and solids, you can see that the speed is increasing. Single frequency sound wave, which is pressure density variation, would have the shape of a sine or a cosine. So if we talk about a certain, let's say, 100 hertz wave, so it would correspond to sine or cosine wave like this. So these are called pure sine or cosine waves. So when you have a sine or cosine wave, each of them correspond to a certain frequency. You can see that these up and down are more frequent, and that corresponds to higher pitch or frequency. But in reality, the sound waves, when you hear someone speaking or a musical instrument or any sound wave, in reality, they include combinations of many sines and cosines with different frequencies. So it's rare that maybe only computers or electronic devices, they create pure cosine or sine waves, but in pretty much all the physical objects, they create sounds that include many frequencies together. So what happens if you add them up? For example, if you add these three up, you get a complex wave, as you can see here. So this is the wave that you get when you add those pure sine waves or cosine waves with different frequencies. Different musical instruments sound differently because their characteristic waveform is different. So different instruments, they combine these sine waves with different weights. So they get different shapes. For example, for flute, it's like this. Clarinet, oboe, saxophone, they all have different characteristic shapes. The reason for that is, again, they combine different frequencies, pure sound, sine or cosine waves, with different waves. So some of these instruments, maybe they include more 100 hertz than others, or some maybe they include more of 300 hertz than 200 hertz. So it basically depends on the instrument. And that's pretty much the reason why we get different sounds from different instruments. Okay, here's an example about the speed of wave. So the sound of a thunder takes 5 seconds to reach you. So there's a thunder happens here, and you are in your house here. So the speed of sound, so because the speed of sound is not infinite, so it takes some time, and it says here it takes 5 seconds to reach to you, that the sound reaches you in 5 seconds. So how far away was the lightning? What is this distance from the lightning to your house? Here's a solution. So the light from the lightning moves at the speed of light, which is 300,000 kilometers per second, which means light travels, for example, for 300 kilometers, it travels in 0.001 seconds. Since this is very small time, we can assume we see the lightning without any time delay. So because this is really small time, let's assume we see the light as soon as this lightning happens. Even though it takes some time for the light to travel and reach us, but this number is really, really small, so let's ignore that number. But for the sound waves, they travel in air. Sound waves in air travels with the speed of 343 meters per second. I mean, this number is really, really small if you compare it with this number. So the distance from the point where the lightning happened to the observer is, well, I know the time, I know the speed, so I have to do x equals vt. V is the speed of sound in air, which we know. We know the time. If you multiply them, you will find approximately 1.7 kilometers. So in fact, you can. So basically, you can time the time from the lightning. So whenever you see the lightning, start counting the time until the point that you hear the sound of the thunder. So you can find then this time and multiply that time by the speed of air, speed of sound in air, and you will find the distance from your position to the location of the lightning. Okay, so sound waves can have any frequency. The human ear can hear sounds between about 20 hertz to 20,000 hertz. So we can hear any sound between any frequency between these two numbers. Sound frequency is also called pitch. Sound with frequency greater than 20,000 hertz, they're called ultrasonic. And sounds with frequencies less than 20 hertz are called infrasonic. Ultrasonic waves are familiar from medical applications that probably you've seen one of these baby pictures within the womb of a mother. And elephants and whales communicate in part by infrasonic waves. So elephants and whales, they can hear each other, but we cannot because they use infrasonic, which is way smaller than this frequency. Wave speed, wavelength, and frequency relationship. This one, it's valid for sound waves too. So we know that, we learned that the sound speed in air is 343 meters per second at 20 degrees Celsius. So frequency was related to how many times a wave oscillates in 1 second. And the wavelength is again related to the distance from crest to crest. So the bats, they use ultrasound waves to find their prey. They don't really, at nighttime, they don't really see their prey, but they can sense where they are by using ultrasound waves. what happens is the bat produces ultrasound waves, the green ones. So when they hit an object or a insect, or in this case, in this picture, it's a butterfly, there will be some waves reflected. So when they get the reflected wave, they can actually find the direction and the position of their prey. So they're basically using ultrasound waves to see, quote unquote, see their prey, to find the position of their prey. Now we move to sound intensity. So a truck is more loud than a dog. We measure loudness with sound intensity. The intensity of a sound is basically the amount of energy that passes through a given area in a given time. So let's say there's some loudspeaker here that creates sound waves. If you want to measure the intensity, what you have to do is you have to calculate the energy of that sound waves and divide it by the area, and also divide by the time. So energy divided by time, you can rewrite it as pressure, and remember the unit, the power, and the unit of power is watts. And here's the area. So the dimensions of intensity in SI units is then watts per meter squared. So if the energy is large, then the intensity is large. Or for a given energy, or for a given power, if A is small, then the intensity is also large. So here in this case, the sound produced by a point source is emitted radially outward. So let's say there's a drum here and someone is playing it, so it will produce sound waves. Now look at this sphere, the blue sphere. Think of it as the wavefront of the sound waves. So you play the drum, the sound waves reach here radially outward in a form of sphere. And as time passes by, the sound will go out radially in all directions. So now let's think about this area. The area of a sphere is 4 pi r squared. So if r is large, the area is large. So the sound intensity from a point source will decrease as the inverse of the square of the distance. The reason is that, so I'm going to write this 4 pi r squared in the denominator, which is here. Now, if you increase the distance from the source by a factor of 2, then the intensity will decrease by a factor of 4. So if you are far away from the source, here, this is the distance, then the intensity goes down by the inverse of r squared. So in this table, you see the typical sound intensities. For example, the whisper at 1 meter. So if someone is whispering and you are 1 meter away from them, then the intensity is about 10 to the negative 10th. The normal breathing intensity is 10 to the negative 11th, and threshold of hearing. So this is the minimum sound with the minimum intensity that you can still hear. It's 10 to the negative 12th. If the sound intensity is, let's say the rock concert is 0.1, if the intensity is 1, then after that point, you will start feeling pain in your ear. The jet engine is about 100. So if the sound intensity is really, really high, which is around 10,000, then you could have rupture in your eardrum. So after that point, above that point, it becomes harmful for human ears. Okay, let's look at this example. The person 1, which is here, at a distance from the bird at R1, so this is the distance, 1.66 meters, hears the sound of the bird with an intensity of 2.86 times 10 to the negative 6 watts per meter squared. The question, the first part is, what intensity of sound is heard by the second person who is at, so this is the second person, and this distance is 6.71 meters. So if we know so in the first, so the power is not given. So the distance is given, the intensity is given, we can calculate the power, that's one way to do it. Or what we can do is, we can write the intensity formula for the first person. It's power divided by this 4 pi r1 squared. Why are we using the area of the sphere? Well, this is the area of the sphere, because we have a point source. The source is at this point. So it's not a distributed source. You know, we don't have multiple birds at different places. We have just one bird at one point. So the sounds from it, they will go out, even though we hear these are like two-dimensional. They look like two-dimensional, but it's actually the sound waves go out as a spherical shells. So like these. So that's why we are using area of the sphere. So the intensity, the intensity that this person hears is the power of the bird. It's the singing power, or the power of the sound that comes from the bird, and it's divided by this term. For the second person, the intensity of the sound they will hear, it will be again the power. Power is the same because the source is the same. And now instead of R1, we will have R2. Now, if I take the ratio of, calculate the ratio of these two, so I would write I1 divided by I2. So this will be P divided by 4 pi R1 squared. And the second one would be, again, P divided by 4 pi R2 squared. Now, P's are the same, so I can get rid of them. I can get rid of 4 pi's, so this will be R2 squared divided by R1 squared. So from here, I have to, so what's asked is the intensity that the second person hears. So I'll solve for I2, and you get this. So we know the intensity that the first person hears, it's here. We know R1, and we know R2. So from here, we can find the intensity of the sound that this person receives is this number. Now, the second part of the question is, what is the power output of the bird's song? So basically, power is, again, energy divided by time. So in other words, what is the energy of the sound that the bird produces in 1 second? That's another meaning of power. So if you look at, so we can calculate it from here. So power is I1 times this term. So we know I1, it's given in the problem. The distance is given in the problem. If you calculate the power, you find this number. Human perception of sound is not linear in intensity. What it means is, if you double the intensity, that means you double the power, you double the energy of the sound. We don't perceive our perception of sound, or the loudness, what we feel as loudness, it does not double. So our perception, human perception of sound, and the intensity they are not linear. For example, to perceive the sound or music twice as loud, the intensity of that sound should increase by a factor of 10, not 2. Therefore, we use a logarithmic scale to define intensity values. So, measure of power per unit area, that was intensity. So, power per unit area. But the measure of loudness is something about our perception. So measure of loudness perceived is, it's called intensity level. So don't confuse these two. Intensity is about the power or the energy per time per area, but intensity level, it measures the loudness as we perceive it. So intensity level is shown by beta. It has the factor of 10 times log at the base of 10, intensity divided by I0. So that I0 is kind of the reference. So I will talk about it here just in a second. But so the unit of intensity is decibel. Deci is basically because of that 10 that's added to the definition. So deci means 10. And bell is due to the inventor of the telephone, who is Graham Bell. And the unit is shown as dB. It's dimensionless, just like radians. It still has a unit, but it's really dimensionless. 10 doesn't have any dimension. And this function log of this number is, again, dimensionless. So what is that I0? I0 is, it's this number, and it was in the table in the previous slide. It's the faintest sound intensity that can be heard by a human ear. So it's the faintest, it's the minimum intensity, the sound with the minimum intensity that you can hear. So let's say if this intensity, let's calculate beta for certain values. If this intensity is this number, and notice that I0 is always, this number is, I0 is always in the denominator here. It's part of the formula. What changes is we just change I. So for different I, we calculate different beta values. So if I is equal to I0, let's say someone is maybe whispering with this minimum intensity. So then, so we got here I0 divided by I0, which you get 1, and log 1 is 0, so you get 0 decibel. It's actually here. So we mapped this minimum value to 0. Now, what happens if someone is speaking maybe at the intensity of, maybe again still whispering, but at the intensity of 10 I0. So basically we are increasing the intensity by a factor of 10. And let's see how the intensity level, which also means loudness, this is about our perception. Let's see how it changes. So now we have 10 I0 here. And so 10 times log 10, so the base is 10. So this is now 1. So what we find is 10. So in terms of decibel, this is 10 decibels. So if you go to 100 I0, so you're going to have 100 here, 100 and 100. So let's do that. 10 log 100. So log 100 is 2. So you would get 20. So we go from 0 to 10 and then 10 to 20. But if you notice, if you notice that to increase it by a factor of 2, the loudness, to increase the loudness by a factor of 2, we increased the intensity by a factor of 10. So you can see that to go from 30 decibel to 50 decibel, this is a linear scale here, but so this is intensity level, but you have to do that just to increase, to go from 30 decibels to 50 decibels, you have to increase the intensity by 100-fold. To go from 60 decibels to 70 decibels, there's really not much difference, but even for that small difference, still noticeable, but not huge difference, but the intensity, you have to increase the intensity by 10-fold. So that's why we talk about the logarithmic scale. When you change the knob of a volume knob to increase or decrease the loudness, you actually, the intensity, so you change the intensity level, but not linearly. So you change it a little bit, but let's say you increase the volume. So to increase the volume from 30 to 50, the intensity is actually increases by a factor of 100-fold. So this volume doesn't control the intensity linearly, it controls the intensity level or the loudness linearly. So the volume linearly depends on the intensity level, not the intensity itself. So if you want to change the loudness by a factor of 2, you have to change the intensity by a factor of 100. If you change the loudness by a factor of 3, the intensity should change by a factor of 1,000. Or you can think of this way as well. If you increase the intensity by a factor of 100, the loudness only changes by a factor of 2, because log 100 I0 would correspond to, so log 100, which would give you 2. So here's an interesting example. A crying child emits sound with an intensity of 8 10 to the negative 6 watts per meter squared. So we have one child, and let's call this intensity I. So this is the intensity. The question is, the first part, find the intensity level in decibels for the child's sound. So the intensity will be, it's given here, this number. To find the intensity level, again, this is about our perception, it's the loudness. So we have to calculate beta. So it will be 10 times log I is this number, and we are going to divide it by I0, which is part of the formula, and it's this small number. And if you do the calculation, you will find the intensity level or the loudness is, for this child, one child, is 69 decibels. Now in the second part, this is where it gets interesting. The intensity level for, so basically beta, for this child and its twin, both crying with identical intensity. So what happens? What is the intensity? So if you have one child crying with intensity I, if you have two children, if you combine and if you get them together, the intensity that they produce, the intensity of the sound they produce would be 2I. So because intensity is related to power or energy, so if you get them together, then you basically add them up. But the intensity level beta is different. Like, are we going to perceive the loudness here as twice as large? It's actually not the case. Now let's calculate it. Intensity level of two children. Again, here's the formula. So now instead of I, we are going to use 2I. I is this number. So, and if you do this calculation, intensity level, loudness, is 72 decibels. So even though we increased the intensity by a factor of 2, but the loudness increased only just a little bit by only 3 decibels. So loudness perceived by humans from 2 children is not much different than that of from 1 child. So basically the loudness or the intensity level between 1 child crying or 2 children crying, it will be pretty much the same. I mean, 69, 72, not much difference. So here we will move to Doppler effect. So this is something that you have experienced many times in life. So while a car is approaching you, the pitch meant frequency, as if you remember. So the car is approaching you. Let's say there's a car which is approaching you. So this is the car, it's approaching you. The pitch frequency of its honk, so it's honking. The pitch will sound at a higher tone than a normal. But when the car is receding from you, so it's getting away from you, the pitch of its honk will sound at a lower tone than normal. So this is called Doppler effect. Let's see this video and hear the sound, how it changes as the car is approaching and it's receding. And why is that happening?
This. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
Okay, let's maybe hear one more time the honk.
This. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on?
Okay, let's try to explain this. So due to the movement, so think about this pickup, and it's honking. So the sound waves are, so normally if you have a pickup that's not moving, the sound waves would go out in a symmetric way. But if the pickup is moving forward, what would happen is in the front, so due to the movement of the pickup below this one, the wavelength of its honk sound in the front of the pickup is smaller. You can see that the wavelengths are actually smaller. So one wave, so these wavelengths are like so this is like going up, down, up, down. So this is one crest, another crest, another crest. And if you measure the wavelength between them, they're actually smaller than those between these crests. So that means if the wavelength is smaller, then that means high frequency. Why? If you remember this relation, speed equals a wavelength times frequency. So the speed of air here is fixed, 343. So if the wavelength is smaller, which is the case in the front, then the frequency is larger. So here there's high frequency, so this is high frequency than normal. And the wavelength of the honk at the back is longer. So here the wavelengths are longer. So that means if the wavelength is large, then the frequency is smaller. So here we have low frequencies or low pitch. So we can have the same effect if the source, a similar effect, or if the source is stationary, so we have the radio here, and so since it's not moving, the waves are going out radially in a symmetric way. But in this case, so the source is stationary, but the observer is moving. So if the observer is moving in towards the radio, the observer will observe a wave crests more quickly than normal. So he will observe a higher frequency. So normally if he was not moving, he would observe the crests, let's say in every 1 second, maybe. If it's a 1 hertz, let's say, wave, well, we cannot hear 1 hertz, but let's assume. But if he is moving with speed u, then he will actually get the crests, the successive crests, in a time that's less than 1 second. So if something is happening more frequently, if the period is less, then he would perceive the frequency of the sound as at a higher pitch. So in the first case, here, the observer is stationary and the source is moving. In the second case, the source is stationary and the observer is moving. So in each case, in both cases, we have a similar effect. So the most general formula is this one. So here F is the source frequency. So it's either from the hunk or it's either from the radio. So this is the source frequency. V is the speed of air. It's a fixed number. U0 is the observer speed. So in this case, U0 is 0 because the observer is stationary. But in this case, U0, there's some U0. U sub S is the source speed. Here there's some source speed, it's moving with certain speed, but in this case, in the second case, the source speed is 0. And in general, they may both move towards each other or away from each other. So the most general case is that you have both U0 and US non-zero. And this is the frequency that the observer observes. So as mentioned in the previous slide, the observer, if there is movement involved, the observer will not hear the original frequency, but the frequency, so the observer will hear either a lower pitch or higher pitch. So in this formula, when you use this formula, U0, V, and US, they're all positive values. So if the car is going to the right or to the left, it doesn't matter. You don't put a negative sign, so you always use positive values. So you can think of these as the absolute values if you want. So in the numerator here, plus sign, you have to use plus sign if the observer moves in the direction of source. So the observer, for example, here, it moves in the direction of source. You use positive sign. If the observer moves in the opposite direction, so it goes away from or recedes from the observer, then you would use a negative sign. For the denominator, you would use negative sign if the source moves in the direction of observer. So this pickup is it's getting closer and closer to the observer. So you would use in the denominator a negative sign. But if this pickup was going to the left, which in that case would get away from the observer, in that case you would use a positive sign. So here's an example. A street musician sounds the A string of his violin, producing a tone of 44 hertz. So so F basically It's the original or the source frequency. So if you're standing here, then not moving, so the source is already not moving, you would hear 44 hertz. But the cyclist here, cyclist, what frequency does a bicyclist hear as she approaches the first case, and if she recedes the second case from the musician with a speed of 11 meters per second. So first of all, since the source speed is 0, the source really not moving, then we can get rid of this term. And division by 1 is trivial. So our formula is only the top part. Now, if you remember, if the observer is getting closer to or moving towards the source, we would use positive sign. So that's why for the first case, we have the positive sign. The observer, which is the cyclist here, speed is 11 meters per second. It's given in the problem. V is, as usual, the air sound speed in air. And 440 hertz is the source frequency. And in the second case, because the cyclist is receding from the source, now we have to use a negative sign, and everything else is the same. Here again, it doesn't matter if the cyclist is going left or right. What matters here is you have to look if the observer is getting close or getting away from the source. So that determines these plus and negative signs. So these don't depend on the coordinate to the left or right. They depend on if the observer and the source are getting closer, in that case plus. If they're getting away, in that case, use negative sign. The Doppler effect has many practical applications like weather radar, speed radar, medical diagnosis, or astronomical measurements. For example, measuring blood flow through arteries via reflected ultrasound from blood flow. You can measure the blood flow, like what is the speed of the blood in the veins, how you measure it. Well, what you do is basically, let's say this is an artery or a vein. Let's say the blood moves in this direction. So you send ultrasound waves, and then they will be reflected. Now, the reflected waves, if they will be affected by the flow of the speed of blood. So when you receive those reflected waves, they will be Doppler shifted because of the speed of the blood. So you can, from that, by basically looking at the frequency of the reflected waves, you can determine the speed of the blood. So here, blue and red, they actually show the directions. So one of them is the blood flow, let's say, maybe towards us here, and the other may be away from us. So it's basically they are blood flows in opposite directions. The Doppler effect is also used with radio waves. Even though we are dealing with sound waves here, radio waves are electromagnetic waves, but the idea is the same. For example, you can send radio waves to the clouds, and they will be reflected from the clouds. And by looking at the frequency of the reflected radio waves, you can determine the speed of the clouds. Or in the case of a police radar, so what happens is the police is, by using radar gun, sending ultrasonic waves, and they will get reflected from the car back to the police, to the radar gun that the police holds. So again, so the frequency of the waves, they will change depending on the car's speed. So from that, the radar gun, it can actually infer what the speed of the car. And the police can determine if the driver is speeding up or he is just driving with under the speed limit. So superposition and interference. Superposition is basically the combination of waves. So if you have a wave like this is the wave, one wave. The other one is like this. It's, the positions are different. This has more height or amplitude. When you combine them, so this is the combination, it just becomes like this. Or if they're moving, so they can collide, but they don't really change their shape. So at some point, at some time, the amplitude becomes maximum because we add them up linearly, and then they go through each other. So this is the case if the waves are interacting linearly. Maybe surface waves may act like this, or sometimes the sound waves. But depending on the frequency, there may be some deformation because of this collision, but in general, it's a good approximation to assume that two waves, when they collide, we just add them up. So if two pulses combine to give a larger pulse, this is called constructive interference in case A. So the two waves are coming together, and at this point, they add them up. They add on top of each other, and then this is called constructive interference because the amplitude grows. And of course, after some point, this wave now goes in this direction, and this wave goes in this direction. The second option is here. It's if they combine to give two waves, they combine to give a smaller pulse, or sometimes zero. This is called destructive interference. So one of the waves is positive amplitude, the other one has the negative amplitude. When they combine, if the amplitude is, let's say, height is h, if this one also has the same height h, if they combine at this point, what will happen is the heights, the waves, they will destruct each other momentarily for some moment. As you can see that this is zero. So these could be some strings and waves on a string. But after some point, of course, this wave moves this point, and this wave goes now to the right. But the point here is at certain time, there's a time where these two opposite waves meet. And when they meet, because the heights are the same, but they're, the amplitudes are different, then in this case, they can destruct themselves. So this is called destructive interference. So depending on their relative position, now look at this wave 1. So let's call this y1, the amplitude, and this is y2. Now, depending on relative position, there you can think of look at the crests. So at this point, the crests align, they're in line. When that happens, the summation becomes maximum. When they're, if the maximum of the top and the minimum of the top, when they align, then the total becomes minimum, and it's going to happen now. So now the maximum and the minimum are aligned, so you get 0. Now this maximum and the maximum, when the maximums align, you get maximum amplitude in the total wave. So depending on their relative position, it's also called phase. Two sine waves may interfere constructively or destructively. So that also happens in water waves. So if you have two sources, they create water waves here. Let's say something like goes, some object that hits here and that hits here at the same time, which creates these water waves. Now, if you look at here, for example, on this line, you see a lot of crests and minimums. So minimums, maximums, minimums, maximums. So we have high waves. So there's a constructive interference. But if you look at, for example, this line, destructive interference happens. There's really no waves on this line, no waves here. There's waves here, goes up and down, but no waves here, it's flat, and the waves here. So this figure basically shows in water waves, there is constructive and destructive interference, and that happens at different places. Okay, now we move to standing waves. A standing wave is fixed in location, but oscillates with time. Now look at these waves. They don't really move to the left or to the right. In fact, we can think of them as two waves that one of them is moving to the right, the other is moving to the left, and we add them up and we end up with these standing waves. But the standing wave itself is not moving to the right or left. So this is an example. These are, so you have the strings and they're fixed or clamped at the ends to the wall or to some point. So this is an example of a standing transverse waves on strings. The transverse standing waves are found on strings with both ends fixed, which is the case here. But there are also longitudinal ones, as that happens in the pipes or musical instruments like flutes or other pipe type musical instruments. And we will see them in the next slides. But for here, on this slide, we have standing transverse waves. So let's start with the first one. So the first one, it's referred to as first harmonic. The other name for first harmonic is the fundamental. And when you clamp or fix two ends of a string, the minimum frequency of oscillations, the shape for minimum frequency becomes like this. Now let's look at the wavelength. What is the wavelength of this oscillation? So let's try to find it from the figure. Now, so this length is L, but this is half of a wave, right? A full wave is something like this. Let's do it again. This is the full wave. So one wave is like this. And if you measure this distance, it's 2L. The wavelength is 2L. So even though you see half of it, it doesn't change the fact that its wavelength is 2L. So this is the minimum wavelength that that you can see on the system when you have two fixed points and there's a string between them, and if the distance is L, the first harmonic, or it's also called fundamental, its wavelength will be 2L. If you want to find the frequency of that wavelength, then the frequency is basically use this relation. So F equals V divided by lambda. So V divided by 2L, this is the lowest frequency. So frequency means, if you want, so let's start. So you start from here and it goes down and it goes up. So that time is period. Frequency is frequency is basically how many times this starts from here, goes down and goes up in 1 second. So as you can see, this is the lowest frequency. It moves slow. So it takes about maybe 2 seconds for this one, for one full motion, or maybe 3. So this one has, its frequency is about, I think, 1 second. So think about, for example, this point. Measure the time from top, down, and top. So that will give you the period divided by, so 1 hour period, it would give you the frequency. So the frequency here is high because you can see that it's oscillating faster in comparison to this one. So the frequencies, they increase. You can see that V divided by 2L, V divided by L, 3/2, 2. So the frequency increases this way. But if you look at the wavelength decreases if you move this way. 2L, L, 2L divided by 3. And we can see that the wavelength is, in fact, here we have one full wave. So the wavelength, and this distance was L, and the wavelength is L. Here we have how many waves? Well, from here to this point, it's actually one wave, and there's a half wave here. So it's not, so the wavelength, so we have 1.5 waves here for a distance of L. For a distance of L, we have 1.5 waves. So that means the wavelength here is 2L divided by 3. And if you look at the fourth harmonic, we have one wave from here to here, and the second wave from here to here. So this is a full wave here. So this distance, lambda, would be, well, the whole thing was L, and it's half of it, so L divided by 2. So these overtones, they're called second harmonic, third harmonic, and you can go up to infinity. So you can create like more higher frequency, lower, smaller wavelength waves, and their frequency would be higher. But there's a minimum. There's no maximum for the frequency, but there's a minimum for the frequency. It's this one. And the reason for that is if you have a string of length L and two ends are fixed, this is the only wave that you can create. This is the wave with the smallest frequency that you can create. And this is the shape. So we have this relation, if you remember, that relates the frequency and the wavelength. This is the speed. This is the speed of a wave. Even though the waves here are not moving to the left or to the right, still the speed is defined. And that speed, if you remember, it depended on the physical properties of the string. So the tension in the string and the density, the mass density of the string. The other thing that you have to notice here is the frequency. If you go from F1, which is fundamental, or the first harmonic, to F2, the difference between them is exactly, so if you do V divided by L, V divided by L minus V divided by 2L, which is V divided by 2L, and this is already F1. So the difference between frequencies are always F1. So that means if you want to calculate F3, you can use this formula, or you can just say F3 is equal to 3F1, because the difference, so this is so this is F1, this is 2F1, so this becomes 3F1. But if you want to find the frequency or the wavelength of any harmonic, let's say nth harmonic, then you can also use these formulas. You can see that when you put 1 here, you get V divided by 2L. When you put 2 for n, here you get 2V divided by 2L, that's V divided by L, which gives you this one. And here n could be 1, 2, 3, and so all the positive integers. If you want to find the wavelength, you can use this one. And as you can see, if you put 1 for n, you get the first one. If you have n equals 2, you get the second one, so on and so forth. Okay, so let's talk about nodes and antinodes. So here we have the third harmonic. So it's a one-dimensional wave. So the amplitude is, of course, in the transverse direction, but we have the string itself is axis in one dimension. So the points that the points whose amplitude is 0 are called nodes. So the amplitude here is always 0, right? Because the string never goes up here or here. At this point, it's always 0. At this point, it's also 0. Also, if you look at this point, the amplitude is again also 0, also this point. So these are called nodes. The antinodes, they are the points where the amplitude becomes maximum and minimum in time. So this is an antinode. This is an antinode, and this is also an antinode. So this was oscillations in one dimension. We can also think of oscillations in two dimensions. So here we have, you can see that oscillations of a rectangular membrane. Let's say these ends are fixed, glued. So this is like a drum. So you can oscillate up or down. You can see that the lowest frequency, this is the fundamental or the first harmonic, it's really slow because the frequency is low. But when you go to higher harmonics, one cycle of motion takes less time. So the period is small. That means the frequency is high. So here it's more frequent. The up and down motion is more frequent in a given second, but here it's less frequent. It's slow. You can have oscillations like these. So the green, when green goes down, green basically means down, and purple means up. So this part goes up and this part goes down, and vice versa. So just to remind you that the frequency is related to time. So it's basically how many times in a second the amplitude at a given point goes from max to minimum and then back to maximum. So let's choose this point. So the frequency is how many times this starts from maximum, goes to minimum, and then comes back to maximum. So it's one full motion. So frequency is how many full motions in 1 second. So that's frequency. If you remember, period was the time for this motion. So go down and up. That will be the time for one motion. And the wavelength is, again, it's related to space, not time. It's the distance from crest to crest. So the crest is here, the other crest is here. So this is the wavelength for this wave. Okay, we have an example here. One of the harmonics on a string. So we don't know, it could be the first harmonic, the second harmonic, the third harmonic. We don't know which one it is, but one of them on a string has 1.3 meter length. The string length is 1.3 meters. Okay, so L is 1.3 meters. So that harmonic has a frequency of 15.60 hertz. We don't know if it's F1, F2, F3, it could be anything. And the next higher harmonic has a frequency of 23.40 hertz. So in the first part of the question, find the fundamental frequency. So it's asking what is F1. Now we are going to use these formulas that we learned in the previous slides. So the difference between two successive harmonics. So let's say this one is Fn. If I call it Fn, I don't know what n is, but if that's the case, then I have to call the next harmonic Fn plus 1. So these are successive. So if I use n here, I have to use n plus 1. And what I learned in the previous slides, that the difference between two successive harmonics, n and n octave, NR1 is the fundamental first harmonic. So it's the fundamental frequency, or the other way, the other name for it is the first harmonic. So from the formula, if Fn is given by n times the speed of sound, or speed of wave, in this case we have n divided by 2L. So for n plus 1, it will be just, have n plus 1 here. Now the difference between them, because they are successive harmonics, the difference between them would be equal to, so you can calculate it from here, it will be V divided by 2L, because this one and this one will go away, so what's gonna left will be this part. And we know that the difference between two successive harmonics is equal to F1. So we showed this in the previous slides where we had, if this is F1, we learned that this would be 2F1 because the difference was always F1, and the next one would be 3F1, and always the difference was F1. So we know that difference is equals to F1. So now if you do this subtraction, so we know that the higher one is 23.40, the lower one is 15.60. So if you find the difference, you find 7.8 hertz. So that gives you the fundamental frequency, or the first harmonic. Okay, now the second part of the question is the speed of waves on the string. Now we can use, again, we're going to use the same formula. We can use n equals 1 to calculate. You can use any n, in fact, but let's use n equals 1 to calculate V. Now we calculated F1 in the previous part of the question. So this is 7.8. We know, so we don't know V, that's what we are going to solve for, and L is given in the problem as 1.3 meters. And if you solve for V, we find the speed of waves on the string is 20.3 meter per second. Okay, so let's talk about musical instruments. So when you play a guitar or any musical instrument with a string, what you basically do is you pluck a string at some point and you just release it. So a plucked guitar string creates a triangle-like wave moving back and forth. So you can see in this video here. So you start with a triangle-like wave initially. When you release it, that it moves back and forth. So it goes forward and comes. So it hits this point because it's clamped. The string is clamped at this point, and it's the same thing in the guitar, right? At two ends in the guitar, the strings are clamped. And at those points, the wave hits when to those points, it goes back. It reflects back. So since it's not a harmonic function, remember harmonic meant sine or cosine. So here the wave is actually, it's like triangle, it's not harmonic. The wave in a guitar string does not correspond to a single frequency. Remember, if you had sine or cosine, that would mean sine, like here, for example, this is a sine, it corresponds to 100 hertz. Here the frequency is different, but still sine, it corresponds to another frequency. So each sine or cosine corresponds to only one frequency, not combination of them. But here, the string, the plucked guitar string, it doesn't create, and this person doesn't create a sine or cosine wave. So then this wave, the sound that's coming from this wave is not, it doesn't have single frequency. It's actually, the sound that comes from the string, it will be a combination of several harmonics. So it will be a combination of different sine waves. And remember this figure, when you combine different sine waves with different weights and frequencies, you get a complex wave. So a note in a guitar string, let's say you play a note, but that note in a guitar string includes not just one frequency, but it includes several harmonics added together. So here in this animation, you see the triangle-like black wave is the physical wave from the plucked string. And the colored ones here, they are the harmonics or the sine waves that make up the black triangle wave. So you see in the animation, the triangle-like wave, it actually, you can think of it, so that the complex wave, you can decompose it, or you can think of it as a combination of several sine or cosine waves. In this case, both ends are clamped, so in this case, sine waves. So piano has its characteristic shape. You know, the piano shape is always like this, the classical pianos. And the reason for that is it's because high-pitched notes are created by shorter strings. So these are the shorter strings, and you know that these keys, they play high-pitched notes, high-frequency notes. So they're connected to these shorter strings. Why do shorter strings produce high-frequency notes? Because if you remember this formula, so the speed of sound is fixed. You can't change it. If it's the same strings, you can't change it. It's fixed. So the only thing that you can do to get different frequencies, use strings with different length. So that's what happens in these classical pianos. And you have the longer strings here. If the length is large, then the frequency is low. So that's why these keys that are connected to these long strings, they play low pitch notes. So here we have also a keyboard of a piano. So here each color, different colors, show different octaves. So this is one octave, this is the other one, and this is the other one. So the letters, they show the notes. In fact, the yellow should start from here. So this is one octave, and from C to B, this is another one, and this is another one, and this is another one. So different colors show different octaves. The frequency of the same note. So we have a C note here, middle C. Its frequency is here, 261.7 hertz. So but we have C's at other octaves as well. So the frequency of the same note in the next octave up is twice as large. So if the middle C has this frequency, in the C in the next octave up, it will be twice as large as this frequency, and indeed that's the case here. So these two frequencies, they correspond to different overtones, or they're also called harmonics, as we learned, of the same musical tone. So these are C, this C, they are the same musical tones, but they correspond to different overtones. So 3 factors determine the pitch, or the same thing as frequency, of a vibrating string. One of them is the mass per unit length, or the mass density. The other is the tension, which you can change by playing with these things. You can change the tension in the case of guitar. And the other thing that the pitch depends on, it's the length. Why? Because you can see that the frequency depends on the length. So remember that mu, which is the mass density, and the tension, they determine the wave speed via this relation. So the pitch depends on V and L, so the wave speed, and the length of the string by this formula, which we learned in the previous slides. So in order for different strings to have different fundamental frequencies, the reason that you have different strings in a guitar, for example, 6 of them, you need different fundamental frequencies. So you want each string to have their first harmonic, the fundamental, to be different, to have different frequencies. So for that, they must differ in length or linear density mu. So if you look at F here, Fn equals n divided by 2L. So this V, we can rewrite it as F divided by mu. So the frequency can depend on either we can have different length, the strings with different lengths, or in different mass densities. Of course, we can also tune the tension, but that's not enough to change the frequency, the fundamental frequency, or the first harmonic by a large amount. So a guitar has strings all of the same length, so we can't really, as in the case of the piano, we cannot, in the guitar, we don't use strings with different length. They all have the same length. So then the only thing that I can change is, so I can't really change for the guitar's length, then I have to change mu, the mass density. So the only way to have different fundamental frequencies for different strings is to have strings that vary in their mass density. And indeed, that's the case. If you look at the guitar strings, the density, or you can think of this, let's say, what is the mass of the strings for a given length, let's say 2 centimeters or 3 centimeters. This one has the largest mass. So here mu is large mu. Here mu is small. Again, what happens if you have different mu's? Then different mu's mean it means different. You can get different frequencies. Now we move to longitudinal standing waves. So we talked about the transverse standing waves on these strings. Now let's move to longitudinal waves, standing waves. And they can be excited in columns or created in columns of air, such as soda bottles, woodwind instruments like clarinet or flute, or organ pipes. So when you blow over an opening of a bottle, what happens is you create pulses here, and those pulses, they have certain fundamental or harmonic, certain frequencies, and you hear certain sounds, and the frequency of the sound, the characteristic frequency, it depends on the length of the bottle. So if you look at these animations, so the first harmonic, now we don't have transverse waves, but we have longitudinal waves. Now this part is closed. But this part is open. That may be a piston, or it could be completely open. So what happens is you can see the oscillations left and right, and if you go to higher harmonics, the oscillations are more frequently. Now, what you have to notice is certain particles at certain points don't really oscillate. They are just stationary. For example, here, the particles here at the end of the tube, they don't really go left and right. In fact, well, they can't because there's no place to go to the right because it's closed. So if you plot the longitudinal oscillation amplitude, which means how much the particles go to the left and right, at this point it's 0. So this is 0. And if you move to the right, to the left, you can see that, for example, these particles move this much and then come back this much. So they move a little bit to the left and right. So there's some oscillation amplitude. And if you look at all the way to the open end, they actually move from here all the way to here. So they move left and right this much. So the oscillation amplitude here is the maximum. This is the first harmonic. Let's look at the second harmonic. Again, the particles here are not moving, but that's not that point. If you look at also this point, the particles here are also not oscillating. So these are the nodal points for longitudinal waves. If you look at this here, the plot, at this point, it's 0. So the meaning of these plots, they show longitudinal oscillation amplitude. So the height or the y-axis would show the amplitude of the oscillations left and right. So these particles here at this location, they don't really oscillate, so it's 0. Also here, they don't oscillate, it's 0. This point oscillates at max. So the particles here, they are the particles that oscillate most. So you can see that the amplitude is maximum. Also, the particles, the location of the particles that oscillate the most is also here. And you can see that the amplitude here is also the maximum. If you look at the higher and higher harmonics, let's look at the nodal points. Again, the particles at this point, they don't really move. Also, the particles in this line, they don't move. So these are the nodal points. These are nodes. So these particles don't move, but the particles that move the most are the particles that are here, and also here, and also here. And you can see the amplitudes goes all the way up to the maximum. And the other thing that you can notice is that for the first harmonic, the movement is slow. So the frequency of one motion is lower. But if you go to the higher harmonics, the movement is faster. You can look at also the bottom plots that you can see that as you go to the right, the frequency is increasing. So all of these animations are for the case where one end is open and one end is closed for those pipes. So that's also the case for a bottle. So we have the same, we have the plots here like organ pipes or pipes where one end is closed, one end is open. So at nodes, so what these blue lines, they're actually showing the amplitudes, longitudinal oscillation amplitudes. So this amplitude is shown here. This one is shown here. This one is shown here. So as you can notice, this is a nodal point. This end point is a nodal point because the particles here cannot oscillate because there's no place to oscillate in this direction. Also, this is a nodal point, which corresponds to this point. There's another nodal point, which corresponds to this point. And A stands here, they stand for antinodes. And if you remember from the earlier slides, antinodes are the points which oscillate the most, or where the amplitude is the largest. So at nodes, which are these points for this frequency, or for the second harmonic, it's these points. And you can see that the nodes, the location of the nodes and the antinodes, they are different for different harmonics. So at nodes, air molecules don't move. Air molecules move at most at the antinodal points. See, or for example, this is an antinode, and you can see that they move, and the oscillation amplitude is large. So the waves within the pipe shown in left here, they indicate the amount of left-right air oscillations at a given point. Well, here it's left-right, but for these columns, it would mean the oscillations in the up-down directions. So the first harmonic is it's like this. So you may wonder why it's 4L. Why the wavelength is 4L? The reason is so this should be antinodal. This point, this is open, so the amplitude will be maximum and minimum at those points. Here it's the nodal point. The amplitude is 0. Now if we extend this like this, so from here to here, now it's 2L, but this is half of the wave, right? So one complete wave would, maybe we can plot it this way. It will be like this. Or let's do it again. So this is L. So this is L2. So up to this point, it would be the half of the wave. So another L is here. So up to this point, so maybe 2L will be all the way down here. So it will be like this. So if you look at this, so this is the 0 point. So one wave is actually, the wavelength is 4L. So that's why the first harmonic wavelength is 4L if we have a pipe where one end is closed, the other end is open. The second harmonic is 4L divided by 3. The third is 4L divided by 5. And there's a formula for it, for the wavelength and the frequency. So one end open, one end closed column or pipe. It's the case here. So only odd harmonics occur. So for n here and here, the numbers that we can use is 1, 3, 5, so on and so forth. So we don't use even numbers. So in the next slide, we are going to consider the pipes where both ends are open. So this one was open and closed. So let's move to the next one. So here what we have now, open end and open end. Remember, the open ends are always at antinode. So the amplitude, if this is a 0 point, the amplitude can be maximum at the antinodal points. And at the nodal points, the amplitudes are always 0. Of course, the position of the antinodes and nodes, they depend on the wavelength or the frequency. Now here, the minimum wavelength, or the wavelength of the first harmonic is 2L, not 4L, because if you complete it to one wave, like this, and this part would be this. So now look at this one. This is one complete wave. So if this is L, this is L divided by 2, and this part is also L divided by 2, so it's 2L. So the first harmonic, or the fundamental, it has the wavelength of 2L. And the formula for this is 2L divided by n. Now in this case, if both ends are open, then both odd and even harmonics occur. So it's not going to be only odd or even. So for open and open case, we can use, so we will use all n values, all positive integers. Now, one application of this is actually the organ pipes and the pipe organ, musical instrument. It uses a variety of pipes of different length, and you can see them here. There are some short ones and very long ones here. This is the longest one here, and there are also like the short ones like these. So some of them are open at both ends, so just like these, and some others are open at only one end, which are like the ones that in the previous slide. So when a key is pressed on the keyboard is here. So basically air is forced through the pipes. So there's always air pushed through the pipes. Those airs back in the times were pushed by humans, but now there may be some pipe organs that use motors to push the pump air. So when you press the keyboard, a key on the keyboard, air is forced through the pipes, and pipes of different lengths. So depending on which key you press, and because you also have different pipes of different length, you can produce different tones or frequency. So you can produce different notes. Now, in this example, we have the soda bottle. So an empty soda pop bottle is to be used as a musical instrument in a band. Probably you've made this experiment at home at some point. In order to be tuned properly, so tune means getting it to the point where it gives you the tone that you want, a certain frequency. So in order to be tuned properly, the fundamental frequency of the bottle must be 440 hertz. So you want 440 hertz from this bottle. So the top is open, the bottom is closed. So it's the first case that we discussed. So in the part A, the question is if the bottle is 26 centimeters tall, so H is 26 centimeters, how high should it be filled with water to produce the desired frequency? Treat the bottle as a pipe that is closed at one end, the surface of water. So if you put surface of water, so since the water will not oscillate as air, so it will act as if a closing here. So and open at the other end. So this part is open. So now, so this is the formula for, so we had 4L, if you remember, for the case closed for the pipe. One end is closed, the other is open. And also, if you remember, we could only use the odd numbers. So the fundamental frequency is always n equals 1. So if you want to calculate F1, it will be V divided by 4L. And you want the fundamental frequency, which means n equals 1, of the bottle to be 440. So you want this to be 440. So let's plug 440 for F1. V, well, we are dealing with air here, so it's going to be the speed of sound in air, 343 meter per second. And in the denominator, we have 4L. So if you calculate L, you find 0.195 meters, or in other words, it's 19.5 centimeters. So you need the opening, the open part to be this long. So this will be, so L is basically 19.5. So this is not going to be the, so this is going to be the length only of the section where the air is inside, so nothing else, not water. So the whole length of the bottle is 26 centimeters, then the question is how much water or up to which height the water should be added. Well, you can basically subtract 19.5 centimeters from 26 centimeters, and if you do that, you will find 6.5 centimeters. So if you fill this bottle up to with water up to the level 6.5 centimeters, then this length you get 19.5 centimeters, and it will give you for the fundamental frequency exactly what you want, which is 440 hertz. Now the second part is, what is the frequency of the next higher harmonic for this bottle? So basically, what is the next harmonic? Let's think about first that. Only odd harmonics are allowed for open bottles. So the next harmonic is not F2, because that's not allowed for these open bottles. The next harmonic is n equals 3. So it's F3. You can use the formula if you want, or you can just write 3F1. So F1 is 440. It's mentioned in the problem. So multiply by 3, what you find is 1320 hertz. That's the next harmonic, which is F3. So if you blow air from here, most probably you are not going to create only F1 sound with F1, but it will also have contributions from F3, F5, and all other frequencies. But usually the fundamental frequency will be the most dominant frequency of that sound. Okay, finally, we will now talk about beats. So if two close frequencies, F1 and F2, here they could be like 440 hertz and 441 hertz. They're really close. The difference is only 1 hertz. And 1 hertz means, okay, we are going to come to that point. If two close frequencies, F1 and F2, are played at the same time, let's say you have two speakers, okay, one of them is playing sound with frequency 440, the other is playing with 441. Now the total amplitude of the two waves, something interesting happens. Total amplitude, you can see that, let's say this is 440, this is 441, just a little difference between them. If you combine them, well, if you play them at the same location with two different speakers, they will combine and they will create this shape, this envelope. And in time, that envelope, or the sound, the amplitude, it will oscillate at the low beat frequency. So in this case, it will oscillate with 1 hertz. So that's the frequency of the envelope. So now it's 0 here. So after some point, after some time, it goes to maximum, and then it goes to 0 again. It goes to maximum, the amplitude goes to 0. So these frequencies are, so they are 440, 441. So when you listen to this sound, what you will hear the average frequency, the tone. It will be F1 plus F2 divided by 2. So the tone will be, well, they're really close to each other, so you will feel the tone you will hear will be 440.5. That's the average. But other than the frequency, but the amplitude or the loudness, that's the interesting point. It changes with frequency, the beat frequency, and that's the difference for. And in this case, it's 1 hertz. So the amplitude will go up and down with frequency 1 hertz, and that means 1 second, or 1 over 1 second. So the amplitude should go up and down every second. So let's play this video here, and you will hear those beats. Again, the beats are not the frequency of the tone itself, but the frequency of the amplitude or the loudness that's going up and down. So let's play it. So the beat frequency is basically, as you heard, is the frequency. It's a small frequency. It's the difference between the two waves. And that small frequency, you don't really, so in this case, it's 1 hertz, or in the second example, it was 3 hertz. It's not the tone, it's not the frequency of the tone that you hear, it's the frequency of the amplitude going up and down. But the tone is still around 440. So that's the end of this lecture.